All right, so I haven't shared the screen again. Just got disconnected again. Okay. Okay, we are back on business. Okay, so one second. Okay, you need just look at the year of the when the virtual work was invented. 1717. So it's like 300 years ago. John Bernoulli invented the method of virtual work with a very, very beautiful concept. Simple. External work is equal to internal work. Okay. So generally, when you consider the work is of course the distance that your force travel. So if I attach the force here at the end of the structure and the deformation occurs, you're going to have the work caused by the movement or the deflection of the structure or the deformation, whatever you want to call it. So that's a simple concept. But in general, if we look at it from the beginning, the work is not constant because you need to increase the force from 0 to wherever it is, like P and then P plus delta P. So that is the idea of the work from 0. And you can use the same if you attach the force here, and then you can calculate the deflection of this, which is if the load is N, your deformation of this rod is NL over AE, right? So the work is the force itself multiplied by the distance that it has to travel, which is the deformation of the structure. And because the force is coming from 0 up to N, so you have a half in front. So that becomes the work done by the force. Okay. And we're not using that directly, but we are going to look into the principle of virtual work. Okay. Now, you all know what virtual means. It's the opposite of actual. Okay. And we now use the principle of virtual work that the work done externally must be equal to the work done internally. The work done externally generally is the work of the external force. Work done internally is, of course, the work done by the internal force. But sometimes we need to look at the internal force as the stress. Okay. So now let's take a look at this. This is a very useful because this is how we civil engineers employ the principle of the virtual work. So let's say I have a structure, the blue one that you can see now. It takes me a while to draw this picture, I have this blue structure. And then I have the external load, any shape or form, just any arbitrary load. Okay. And before deflection occurs, I attach the imaginary load here equal to 1 to wherever I want to attach. Okay, in the direction that I want to know, direction that I am interested in. Okay, so to speak. So when we actually load the structure, of course, the deformation will occur. So this load that I stealthily attached to the structure before the deformation occurs will travel with the distance equal to the deformation of the structure itself, correct? Remember, I attached the load in the direction that I am interested in. So when the deformation occurs here, it occurs in the direction of the load. And let's say this deformation is equal to delta. So the work done by this virtual load, it's not actual. Remember, it's the load that I sneaked in and attach it to the structure. The actual load is this one that forces the structure to deform. This is our imaginary load. It's attached onto the structure. So when the structure deforms, this virtual load will displace with the exact same amount as the deformation of the structure. Okay, so this is the displacement. Delta here, same delta. So you can guess now that the work done by this virtual load is equal to the load itself multiplied by this delta. And of course, it is called the virtual work. Is there any question? Any question? So we are crystal clear, right? Now, so I already said this, the structure will deform delta because of the actual load. See? So the virtual load will have the work. So the work done by the virtual load, what you call the virtual work, becomes the external virtual work. And simply because we can imagine any load, so we imagine 1 because it's the easiest thing, right? Please don't imagine 0 because it's nothing. No? So this is your virtual load. That is the displacement of the structure under the actual load. So the virtual load multiplied by the distance that it travels gives you the external work. Okay? But when you apply the virtual load, when you consider the virtual load alone, your structure will respond to that. There must be the reaction, the internal force caused by the virtual load. So that becomes the virtual response. We call it U for now. U is not actual. It's the virtual response of your structure due to the fact that you attach the virtual load on it. But because you have the internal virtual load now, the work done by it is the virtual response multiplied by the actual internal displacement, because this is the internal response caused by the virtual load, right? Then, therefore, the work done by this internal response must be the internal displacement as well. But that's a basic concept, and you should know that this one, I keep painting it, is our target in our calculation. You know this because you assume the virtual load equal to 1. And when you have the virtual load acting on it, you can calculate the virtual response. And you can calculate this. So in the end, delta, that is our target, can be obtained. Okay. Or in terms of moment, instead of having delta, you have zeta or rotation instead. Okay. Sounds a bit confusing. Probably, but let's say we are going to get into something more specific now. So the first thing, the easiest thing to see is the calculation of the truss deflection. Okay, so let's say we want to know the deflection of the truss. That becomes our target. We want to know the deflection of the truss. So we would apply the virtual load here in the direction of the deflection that we want to know. in the direction that we want to know. And at the location that we want to know. So these two things go together all the time. So when somebody does not have a clear picture of the virtual work, they will just start off by applying the unit load at the wrong location and the wrong direction. Okay, so let's say I am going to try to swap this with this, okay? Let's say I have a simple truss. Too simple, like this. And then I have the load. Let's make it more complicated, okay? I want to know how much the truss deform. Okay, I want to know how much the midspan deflection of this truss is. This is my actual load, okay? So what I can do is that I will, before the deflection occurs, I will attach the imaginary or the virtual unit load at this midspan in the vertical direction. Okay, so now I have this. Okay, with my, say, imaginary load, my virtual load here. So when the deflection occurs, this multiplied by this deflection becomes the external work. Can you see that? Okay, so now I think the external work is out of the way. So let me recap it here somewhere. So the external work is clearly equal to this virtual multiplied by this, sorry, the color is too similar, the midspan deflection. So that is the external work taken care of. So what becomes of our internal work now? When I apply this virtual unit load here, I will have the internal forces at each member in the truss, right? So let's call it, what do I call it? Okay, N, right? Here called N. So I may have here N1. This is probably N2. This is probably N3, N4, and then N5. Okay, because of course you can perform the analysis on this because you apply the unit load. So the truss must have its own equilibrium under the unit load. So we can easily analyze these internal forces. Remember that this is what we call the internal response to this unit load. Sorry, okay. So N's, or maybe I should say Ni. Oops. Internal response to our unit load. So what would be the work of each and every one of them, the work would be this N multiplied by the internal displacement. That is now the deformation of each member under the actual load. Okay, now we go back to the actual load. You can see that again, this actual load will also cause the internal response. Let me use green. So you can analyze the actual load to obtain the force, right? N1. But before I write N2, N3, and so on and so forth, I'd like to stop here and point out that when you know this actual internal force under the actual load, can you calculate the deformation of this member? Of course you can. So let me write it down here that internal force will give you internal displacement. If you are a good student, you should be able to recall this. But if you, I'm not going to say bad student, but if you're a normal student, you will not recall this, okay? The displacement of any axial force member is, if this is N, if this is P, it's P, if this is L, PL over AE. Of course, you know the length. Of course, you should know the cross-sectional area. Of course, you should know the material property. So from this N1, you would be able to obtain the internal displacement of this member. It's internal because it's just the displacement of one member in your system. Because your system is now a truss, which consists of too many members, correct? So now, the internal displacement of one truss member, this member becomes N1. Let's call that member N1, right? You write that again, it slips. N1, L1 over A1, and then E. And you can proceed to obtain the same thing. This is going to be N2, L2 over A2, and then E. I write one E because nobody's going to be too crazy to construct truss with like many materials, okay? So this one is going to be N3, L3 over A3, and then E. Then so on and so forth. N4, L4 over A4, and then E. And then this N5, L5 over A5, and then E. So now you know each internal displacement. Now, of course, you can obtain the internal virtual work. But remember, now you have a system because this is a truss that where we have 4 members. So you need to, you know, say sum up all the energy. So for internal energy of member N1, you're going to have the energy equal to the force N1 multiplied by the distance that it travels. So it becomes N1 L1 over A1 and E. That is now the internal virtual work done by member number 1. We can carry on. N2. Likewise, that's the internal response. See, internal response to the virtual load. The work done by it is the force itself multiplied by the distance that it travels. So it's N2 L2 over A2E. Okay, and we keep doing the same until N5, which, you know, the distance becomes N5, L5, A5, E. Or I can simply say that this is, of course, the internal work. Or this can be written in, you know, simple form, sigma I equal to 1 to N, Ni, capital 1, Li over Ai, and then E. See, this is very, very straightforward, but it becomes, you know, trouble for those who cannot analyze the trust. Right? Question, folks? Hello?
Yeah.
Yes? That's not a question. Crystal clear? Perhaps not. Yeah, thanks a lot, Nopudon. Thanks for asking. Thanks for answering. Even though I know you should be okay with it. Junior, third year student, you okay?
Crystal clear, sir.
Huh? Really? Okay. Yeah, actually, it's not difficult. You know, it's just you have. Let me repeat again one more time. You apply the force, your imaginary force, at the location you want to know displacement in the direction you want to know. Remember two keys. Location and direction. You apply that, you're going to have the internal response. Okay. And this is the virtual load. It's not the real load. So the work done by it is this multiplied by the actual displacement that you want to know. But when you apply this, you have the internal response in the pink ones. And so you have the internal load. The internal response, which is also virtual, multiplied by the actual internal displacement, which is the, you know, deformation of each member under the actual load.
Professor.
You know the internal work done by each member in this form, right? Internal virtual response multiplied by internal actual deformation of the corresponding member. You sum them up because it's a work, so you need to have the work of the entire system. Once you've done this, you just use the concept that the external work, sorry, you mean that, is equal to the internal work. So this one is equal to that. There you have it, the deflection. Is there any question?
Question, sir.
Yes, please.
Can we apply the virtual force at the member, but not at the joint?
Ah, you know what? I like your question, but because I can point something back at you. If I apply the force here, oops, like this is your question, right?
Yes.
Is this a trust?
No, technically.
Technically, no. So it's not a trust. Technically, no. Emphatically, no. If you apply the force not at the joint in the truss, you no longer have a truss system, young man. So your entire system is no longer a truss, right? It's a frame. And it makes your life very, very complicated. But I like your question because you think outside the box. So the answer that you get back, you know, will you know, expose you to new experience. So it's wrong to have the trust that looks like this. It's not wrong. It's not the end of the world either. I can do this, right? But the principle of trust no longer applies to this particular structure. And if you construct this as a trust, which means you assume that everything is pinned, right? That's your basic assumption of the trust. That makes this guy becomes a simple beam, isn't it? And not only that it is a simple beam, it will also have the axial force because everything acts as a truss, right? So I like your question because I know you're gonna suffer from your answer, right? Think about it. And you know, I didn't have time to mention the truss system that I also included in the lecture. In the real world, you know, when you construct a truss as a support for your roof, I think some of the senior will have seen this before because they have been to the summer internship already. Let's say it's this one. The truss in the real world, you know, they construct to support the purlin in the roof system. But when they install the purlin, they just put the purlin here, there, and everywhere like that. Some will accidentally fall on the joint, but many will not. They stand, right? They don't fall down. Correct? All right, senior, have you seen this? Or junior, if you have seen this, this is what happens in the real world. Bad construction, folks. It's bad construction. So, you know, you can just go anywhere and, you know, whenever you see the truss outside the real world now, you just look up and see where they install the purlins. You see this most of the time. So when I go out and I see the truss with the, you know, perfect construction, every purlin is on the joint, I was amazed. Wow, they actually care, you know. Remember steel design? Okay. Yeah. So they don't collapse, but they don't behave as a truss either because of the bad construction. But they don't collapse with many reasons. First and foremost, the roof load is not actually there. When we engineers design the truss for the roof structure, the law says that we need to use live load equal to 50 kilograms per square meter. That's a law. But in fact, this load is for construction because people will need to walk on your roof during the construction, right? So when the installation, when the erection is complete, nobody's there. So the live load is never there unless, you know, somebody is crazy enough to walk on the roof and or you have a party on your steel roof. That may fall down. So it's there simply because the live load is not there. The second is that when you assume that you have the pin joint here, there is no such thing as a real pin or real fix in the world. So you have some kind of stiffness in it that your joint is stronger than the actual pin. So that helps as well. Okay. So now, are we good enough to continue on with another one? Oops, that's the wrong lecture. Okay. What's this? Why do I have, okay, crazy. So that's in a nutshell is the virtual work to calculate the deflection of the truss. So is there any question about this one? We shall see the, I actually have this in the, sorry, that's an old one. Okay, I have the example that is almost complete here. You can try to understand this before we have it, because you know that's the actual load, right? And if you want to know the deflection anywhere, you just say mid-span deflection here. If you want to know the mid-span vertical deflection here, you know you need to apply the unit load here. Okay, and you can calculate the response due to the unit load, and you can calculate the actual deformation of each member, but you need to analyze the truss, of course. Now I have given the response due to the actual load, and I apply the unit load, and I also calculated the response due to the unit load. So you can try to go ahead and do something about it. Okay, we'll do this next week so that you have time for the knowledge, the new knowledge to synchronize, to sink in. Okay, actually the English word is assimilate. Okay, you know what that means, assimilate. Okay, so another thing is that we can also use this virtual work concept. Somebody's crying. I can type the word assimilate. That's a very good word to know. Oops, sorry, it just goes directly to Sita, sorry. Assimilate. You know, your new knowledge sinks in. You need time to assimilate it. Okay. Anyway, we can also use this to the calculation of the beam and the frame. But the thing is that when you apply the unit load here, the internal response becomes the strain at the location multiplied by the force in the cross section. It's not as discrete as in the truss where you have, member discretely. So you can directly calculate the internal work of each member. But in the beam, it becomes a section. So we need to start off by, let's use this color, by looking at the small portion of the beam. Okay, and that becomes that is the force on that location, and that is the strain force, the internal strain multiplied by the internal response due to the actual load is going to give you the internal virtual work, right? So the external work is, I thought I was going to find it here. The external work is going to be simple. It's going to be this load multiplied by that displacement, right? So the external work is just 1 multiplied by this delta. But the internal work will become, you see that dA multiplied by the stress. That's the force. But bending stress is my over I. And dA is B dy, Okay, so the internal response is my over I multiplied by dA. Internal displacement caused by the actual load, delta, is the strain multiplied by dx. Where is my dx? It's gone anyway. And this strain is stress over Young's modulus, right? And stress is my over EI. Notice that I am using the small m here for the virtual and the capital M here for the actual. So this is a strain caused by the actual moment. So it's my over EI multiplied by dx. So when I want the work, I multiply these two terms together. The first term is the internal response. So it's a small m. And the second term is the actual displacement. It's a capital M. We multiply them. So we have capital M, small m. I used to say big M, but that's it's like a truck, right? But big M, small m over EI square. We have 2I now. Multiply by y square dA dx. So 3 integrals. We perform integration. Y square dA is I. Okay. Here, y square dA is I. So 1I is gone. So we now have this at the formula. So the internal virtual work is the integral of actual moment multiplied by virtual moment over EI dx. So when it comes down to the beam, you need to perform integration. And the integration will involve two things. Here. First of all, you need to know the proper domain of your function. If you are going to multiply two functions like this, they must have the same domains. In fact, this is like the basic idea of function, which you probably have learned since high school. Am I correct? I think I am, but I will not say any bad word about you at all if you don't know the idea of this, because it takes me a while before I can see the whole picture of everything. I don't know why I needed to learn function in high school until now, okay? So it explains itself, because you are going to multiply the equation of actual moment with the equation of the virtual moment before you perform integration. So these two equations must come from the same domain. Otherwise, you cannot do it. For example, if you have the moment diagram of the actual moment, the actual load looks like this. Now you know you need two equations, one for this and one for that. But somehow the moment diagram of your virtual load looks like this. You can only have one equation. You can have only one equation to explain this. Or I'm sorry, you need only one equation to explain this linear line, right? But let's say if you are going to write this integral and then you use this equation, multiply with this equation, and then you use the same equation to represent this side, you are completely wrong. So you need to make sure before you multiply them that they come from the same domain with the same origin. Otherwise, you cannot multiply them. And now you know, you see this, you need to be able to write them properly, and you need to be able to carry out integration. All right, that's it for me today. We'll begin. I think you will see more clearly when we perform examples on this one. The trust is easier because say it's discrete. So you just perform basic arithmetics. But for the beams and the frames, of course, things get slightly more complicated because you know, of the internal work. Is there any question? Awfully quiet. So let me stop the record first.